Alternating series. So all the convergence tests that we've studied so far apply only to series whose terms are positive. So in this section, we're going to be dealing with series whose terms are not necessarily positive, and to be more precise, we're going to be looking at series whose terms are going to alternate in sign. Okay, let's take a look at this definition. An alternating series is a series whose terms are alternately positive and negative. For instance, this series that you see here, the series which can be written as the sum of terms that look like minus 1 to power n minus 1 times 1 over n. And if you unravel this notation, it means the first term is when n is 1, right? When n is 1, that thing becomes 1. When n is 2, that thing becomes negative 1 to power 1, which is negative 1 times 1 over 2, so negative 1 half, right? And so on. So as you realize, the sign of the terms of the series are going to alternate because of the presence of this minus 1 to power n minus 1, right? Similarly, a series like this, minus 1 to power n times n divided by n plus 1, this is also an alternating series. Just unravel what this means. It means the first term is going to be negative this time, because when n is 1, that's going to be negative 1. So negative 1 half as a first when n is 1, and plus 2/3 when n is 2, and so on, right? Okay. Before we continue, I would like to take a small digression and talk about this exercise, which is going to be needed in the proof of the next theorem, which has to do with alternating series. Let's prove that if the limit of those terms is equal to L, and what are these terms? These are the terms of a sequence which have even ranks, right? So these are the even ranked terms of the sequence AN. Okay, so let's assume that the sequence of even ranked terms of a sequence is converging to a limit L, and let's assume that the limit as n goes to infinity of those terms. And what are those terms? Those are the terms that have odd ranks, right? In the sequence AN. So let's assume that this is also a convergence sequence to the same limit L. Then we want to show that the full sequence AN is also convergent to the limit L, to the same limit. Okay, so this is what we're going to be showing in this exercise. How do we do so? Well, what does it mean for AN to converge to L based on the definition of convergence? Well, what we want to show is, for every positive epsilon, for every radius, right? For every radius of the ball centered at L, the sequence AN starts being inside that ball from a certain rank on, correct? And how do we write this? So for every epsilon positive, there exists some rank n naught, let's say, such that for every rank after that, the sequence AN starts being inside the ball centered at L and of radius epsilon, which means that the distance between AN and that limit point L is no more than epsilon units away from each other, right? Correct? So this is what we want to show. All right, so our job is to choose a random epsilon, and what we want to find is, based on that epsilon, we want to find a rank from which on this happens. Okay. All right, so let's fix an epsilon that's positive. for this epsilon, what do we know? We know that this limit, the limit of the even ranked terms of the sequence an is L. So we know that there must exist, remember this notation for exist? So there must exist some rank, maybe n1 and n, natural number, such that for any rank after this, the term whose rank is 2n in the sequence an is inside the ball centered at L and of radius epsilon, right? Correct. You agree with me? Okay. Moreover, for that very same epsilon, we also know that the sequence which terms are odd ranked is also no more than epsilon units away from L, starting from a certain rank. So also, we know that there exists another rank, maybe n2, such that from this rank on, the odd ranked sequence, so a sub 2n plus 1 minus L, is going to be at most epsilon units away, right? So this is what we know, because this very first one, this first statement is because that happens. The limit of a sub 2n is L. And the second statement holds because the limit of the odd ranked terms is L. Make sense? All right, and what do we want? Remember, we want a rank and not from which on this sequence, the full sequence, starts being inside the ball centered at L. All right. How are we gonna define this and not? How about you stop the video and think about it for yourself first? The way I'm gonna define and not is, so define and not to be, how about being the maximum between twice n1, you're gonna see why, and twice n2 plus 1, correct? So we know n1 and we know n2 because, I mean, once you fix that epsilon, you know n1 and you know n2. For these n1 and n2, whichever happens to be the maximum between twice n1 and twice n2 plus 1, whichever is the maximum between the two, this is a comma here in between, whichever happens to be the largest among the two numbers, this number and this number, I'm gonna call it n naught. And why this n naught is gonna do the job? Well, now do this. Take an n bigger than or equal to this n naught. So let now n being bigger than or equal to n naught. What do we want to show? We want to show that for such an n, the distance between an and L is no more than epsilon units away, right? So we want to show this then. For any number n you take larger than this n naught. Make sense? We want to show that this inequality holds. Okay. Well, this n that you choose has two cases. There are two cases for it. Either it's an even one or an odd one, right? So case one, so two cases are in order. So two cases are in order. Case one, if n is odd. If n is odd, this means we may write n as twice some natural number plus 1, right? I mean, an odd number is an even number plus 1, correct? Or minus 1. Let's take plus 1 just to keep it as before. Okay? For some natural number k. For some natural number k. Make sense? All right, what do we know about k? Well, we know that n is at least n naught, right? We know that n is at least n naught. So what's n in our context since n is odd? It's this number, 2k plus 1. Correct? So since n is at least n naught, but we know in this case n is 2k plus 1, what can you say then about k? Well, n naught is the largest among 2n1 and 2n2 plus 1, right? So n naught is at least 2n2 plus 1. Is this correct? One more time. N naught is the largest among those two numbers, twice n1 and twice n2 plus 1. So certainly n naught is larger, is at least this, and it is at least this, right? Because it's the largest among the two. So n naught is greater than or equal to this. So we get 2k plus 1 is at least 2n2 plus 1. And if you simplify, this means that k must be bigger than or equal to n2. So, right? I mean, subtract 1 from here, subtract 1 from here, you get 2k greater than or equal to 2 n2. And divide by 2, you get k bigger than or equal to n2. So we have then that k is at least n2. Correct? And now look, since let me box it for you. Since this guy holds for any number n that you choose that's bigger than or equal to n2, k in particular is at least n2. So this guy is gonna hold for k, right? So this guy is gonna hold for k. So I'm gonna write, instead of n, I'm gonna write k. So thus, how about we give it a name? Give it the name asterisk. So thus, by asterisk, we have that because k is at least n2, as we said, this thing holds for when n is replaced by k, right? Because it holds for any n bigger than or equal to n2, in particular the k that we have. So that's going to be a sub 2k plus 1, like this. So 2k plus 1, right? I'm copying from here. Minus L is less than epsilon. Do you agree with me? And what's that 2k plus 1 again? What's that guy? What's that guy here? 2k plus 1? It's the n that we have, right? So this is n. So we can write this, that this is equal to the absolute value of an minus l, right? An minus l. Okay. So look then, what do we have? If n is odd, we managed to show that, remember n is bigger than or equal to n naught. If n is odd, we showed that the difference between the nth term of the sequence an minus l is less than epsilon. Wasn't that what we wanted? Wasn't that what we wanted? Right? Remember, this is what we wanted. All right, are we done? Certainly not, because this is just for case 1 when n is odd. This n that we choose bigger than or equal to n naught. Now the second case is when n is even, right? If n is even. What does it mean that's even? It means that you can write n as twice some number m for some m and as a natural number, right? So n being even means that n is twice m, where m is an integer. In this case, natural number, because n itself is a natural number. Yes? All right, and we're gonna play a very similar game. So I'm gonna leave the rest as an exercise. I'm gonna just say it instead of writing it. So for such, since n is twice some m, for this m, what can we say about this m? Well, the n is at least n naught, and n naught is bigger than or equal to 2n1. So 2m, which is n, 2m is going to be at least 2n1, 2n sub 1, right? And as such, m is going to be greater than or equal to n1. And because m is going to be greater than or equal to n1, this now kicks in, this statement kicks in for m, because m is bigger than or equal to n1, and you're going to get a sub 2m minus L is less than epsilon. And what's a sub 2m? Well, 2m is our L, right? Our n. 2m is our n. So we get an minus L is also less than epsilon. So it's very similar discussion to this, but instead of 2k plus 1, here we're going to have 2m. And instead of 2n2 plus 1, you're going to replace it by 2n sub 1. And the same process, the same thing is going to go. So m is greater than or equal to n1. Instead of using asterisk, you're going to use the one above. And that thing is going to be the same. An minus L at the end is going to be less than epsilon. So for this n, whether it's odd as in case 1 or even as in case 2, that n that you choose bigger than or equal to n0, the desired conclusion is going to hold. And what's the desired conclusion? The desired conclusion is that an minus L is less than epsilon. Okay? So I'm going to write here left as an exercise. The rest of this is left as an exercise, even though I said it all, but as an exercise. So please complete this. It's very useful to write the details. And if you want me to see how you're writing it, I'll be happy to take a look at it. Just send it to me, okay? But the writing should be very, very similar to this, okay, to case 1. All right, so case 1 in concert with case 2 is going to give us what we want, and at the end of the day, the result holds. This green thing holds. That if you have the limit of the even-ranked terms of a sequence and the odd-ranked terms of a sequence converge to the same limit, then what's going to happen is the full sequence is going to converge to the same limit. All right, okay. Let's move on. All right, so let's read this in blue. The following test tells us that if the terms of an alternating series are going to decrease towards 0 in absolute value, remember alternating series is a series whose terms are going to alternate in sign, right? If those terms decrease towards 0 in absolute value, then the series is going to converge. Okay, so here are the details. So it's called, this theorem is referred to as the alternating series test. If the alternating series, this one, whose terms are going to alternate positive, negative, so I'm going to divide it as such, minus 1 to power n plus 1, so this is going to dictate the sign, and this term an is going to supposed to be positive. If that series satisfies the two conditions, and the two conditions are as follows. Number 1 is a non-decreasing, so the an, the sequence an is non-decreasing, non-increasing, I should say, so it's decreasing in some sense. And condition 2 is that those ans goes to 0. So the limit of an is 0. So 1 and 2 combined, you can say it as the sequence an decreases to 0. Under these hypotheses, the series is going to converge. The series this, right, is going to converge, the alternating series. All right, so how does the proof go? Before we actually focus on the proof, let's take a look at how the sequence of partial sum is behaving. Look at this picture. Well, the 0th partial sum, which means we haven't started yet, so we are at 0. And then the first partial sum is S1. What's S1? S1 is when n is 1, that term is going to be just A1, right? So it's A1. And A1 is supposed to be positive, remember? A1 is supposed to be positive. So you move A1 units to the right of 0. You end up somewhere. That's S1. And then to get S2, you subtract A2, remember? S2 is A1 minus A2. So it's S1 minus A2. You move A2. Remember, A2 is positive. All the AIs are positive. So A2 is positive. You're going to subtract. You're going to go to the left of S1, somehow A2 units, right? Somewhere. But you're not going to go too far. You're going to go while being positive. Why? Because A2 is less than or equal to A1. Correct? A2 is less than or equal to A1 because of condition 1. So you're not gonna go to the left too far. You're just going while being positive. All right? So you're gonna land somewhere, and this is S2. So S2 is S1 minus A2. You're back here, right? And then to get to the third partial sum, you're gonna add to S2 A3, and A3 is positive, so you're going you're going right from S2. But you're not going too far from S2. By you're not going too far, I mean you're not going past S1. You're gonna stay to the left of S1. Why? Because you're adding A3, and A3 is less than or equal to A2, right? A3 is less than or equal to A2. Makes sense? So you're not gonna go more than what you came back in some sense. So the worst you go is to get to S1, right? All right. So S1 is gonna be to the left of S3, or S3 is gonna be to the left of S1, or it's gonna be at S1 at the worst case. At worst. Okay. And then you are at S3. If you wanna go to S4, the fourth partial sum, you're gonna subtract from S3 A4, right? And because A4 is less than A3, you're not gonna lose more than you gained by getting from S2. So you're gonna just lose a little. You're gonna lose A4, which is at most A3. So what I mean is S4 is gonna be to the right of S2, and so on and so forth, and so on and so forth. So if you continue in this manner, but keep in mind what happens to AIs. The AIs are gonna shrink, right? The AIs are going to 0. So the successive steps are gonna become smaller and smaller, right? So that bouncing back and forth, they're gonna become smaller and smaller, and they're gonna be like this in some sense. Again, I'm trying to illustrate. We're gonna talk about the details of the proof very shortly, but we're gonna go back and forth. The successive steps are gonna becoming smaller and smaller. Okay. All right. Quick observation. It looks like S2, S4, S6, S8, all these even partial sums are increasing. And in contrast, S1, S3, S5, S7, it looks like these odd partial sums are decreasing. So it seems believable, okay? It seems that there must exist some number S where the even partial sum is gonna converge to, and the odd partial sum is gonna converge to. That's how it looks. Okay? And as such, by the previous exercise that we just proved above, we've written it in green, that S is gonna be the limit of the full partials, the sequence of partial sums. And as such, that's gonna be the sum of the series, and hence the series is gonna converge as the conclusion of the alternating series test. Okay. So based on the picture, I'm gonna build the proof. Let's start. And let's start by looking at the even partial sums. So let me zoom a little bit. And let's start by looking at S. So we look first at the sequence of even partial sums, right? Let's look at this sequence. What's the first term in the sequence? Is when n is 1, right? This is n and n here. So it's S2, which means n equals 1. So S2, what's S2? S2 is A1 minus A2, am I correct? This is the second partial sum. So it's the first term plus the second term, but the second term is minus A2. So we get this. And since what do we know about the AIs? What do we know about the AIs? The AIs are non-increasing. The AIs are non-increasing. So this is going to be certainly a non-negative number, right? So this is going to be certainly a non-negative number since A2 is less than or equal to A1, right? Okay. What can you say about S2? S4. S4 is from S2 you are adding A3 minus A4, correct? And since A4 is less than or equal to A3, what can we say? We can say that this is greater than or equal to S2. Am I correct? Because this guy is non-negative. A3 minus A4 is bigger than or equal to 0. Correct? And so on. And so on. In general, S2n, the 2nth partial sum, is going to be S of 2n minus 2. Correct? We can show it by induction, but it's pretty straightforward in this case. Plus A 2n minus 1 minus A 2n, right? So you add these terms in order to get to S2n from S2n minus 2. And same story, since the AIs is a non-increasing sequence, that guy is going to be non-negative, and as such, this is going to be greater than or equal to 0, right? Greater than or equal to S sub 2n minus 2, because this difference is greater than or equal to 0. So since A2n is less than or equal to A2n minus 1. Makes sense? Okay. All right. So what can we say then? We've realized that S2 is less than or equal to S. First of all, S2 is less than or equal or greater than or equal to 0. So S2 is greater than or equal to 0. And S4 is at least S2. And S6 is at least S4, and so on. And at the end of the day, we have that this sequence is ascending, or this sequence is non-decreasing, and then that's gonna keep going like this, right? Okay. So this is a non-decreasing sequence. A non-decreasing sequence. If we show that it's bounded above, then by the monotonic sequence theorem, this must be a convergent sequence. Correct? So let's show it that it's bounded above. So furthermore, S2n, this is for all n, S2n is what? What's the first term in this nth partial sum? It's A1, right? And then plus A2 minus A2 plus A3. So minus A2 plus A3, I'm going to write it like this. Correct? And this is the same as minus A2 plus A3. Then minus A4 plus A5. If you put the brackets, this is going to be A5 like this, right? So this remains minus A4 plus A5. And so on, minus dot 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 all the way to minus, let's see, the last term is A sub 2n, and before that you're gonna have the guys A2n minus 2 minus A2n minus 1, right? The last one is A2n, correct? And what do we know about all of these? We know that the AIs is non-increasing, right? The AIs is decreasing. So non-increasing because it's less than or equal here. All right. So as such, what do we know about these parentheses then? What do you know about these parentheses? For example, the first one, we know that A3 is less than or equal to A2, correct? A3 is less than or equal to A2. So this means that this guy is non-negative. Similarly here, A5 is less than or equal to A4, which means this guy is non-negative. And so on and so forth. This guy is non-negative for the same reason. For the same reason. Yes? And what do you know about the last one? This is positive. I mean, this is the assumption here. The AIs are positive, right? So what do we get at the end of the day? We have A1 minus what? Bunch of non-negative numbers. So this is at least, this is at most A1, right? This is at most A1. Make sense? Because you're chipping away non-negative entity. This is supposed to be positive. Okay, you're chipping away positive number from A1. So certainly you are decreasing A1, right? So certainly this whole thing is less than or equal to A1. Make sense? So S of 2n for all n is bounded above by A1. What can you infer then? S2n is non-decreasing and bounded above by A1. As such, I mean, it's not, look, it's bounded above by A1, right? Look, this is A1, it's right there. So all these guys are certainly bounded above by A1. So this is not good. I mean, this is not news in some sense. But the idea is that's non-decreasing and bounded above by, and then by the monotonic sequence theorem that we talked about in the sequence section. What can we say? We can say that the sequence S to N, the sequence of even partial sums, is certainly convergent. Right? So this is a convergent sequence. Call its limit S, because that limit exists now, right? We know that this is going to converge, so call the limit to be S. Okay. Make sense? All right. Now, so we know the sequence of even partial sums is going to converge. How about now, as we discussed based on the picture, how about now show that the sequence of odd partial sums is also convergent to the same number S? So next, we compute the limit of the sequence S sub n to n plus 1, the sequence of odd partial sums. Well, what is this? For any n, what is this guy? What is this guy? This is the partial sum of rank 2n, the 2nth partial sum, plus one more term, right? And what's that term? It's the 2n plus first term. It's the 2n plus first term in the series. So this is when this guy is 2n plus 1. If n is 2n plus 1, if you replace this guy by 2n plus 1, that's going to become a positive number, plus 1, right? Because the power becomes even if n is 2n plus 1. And that's going to become a sub 2n plus 1. So you add just a sub 2n plus 1, the 2n plus first element of the sequence an to get from the 2nth partial sum to the 2n plus first partial sum. Okay, and this is for any n. So this holds for any n. How about at the limit? What happens at the limit? So at the limit, we get that when n goes to infinity, that's what I mean, 2n plus 1, that's going to be equal to the limit as n goes to plus infinity of this sum, as 2n plus a sub 2n plus 1, right? All right. And this is the same as, because each one converges, right? The S to N converges, we just showed it above, and the AIs, the sequence AI goes to 0, right? It's by condition 2. It's by property 2 and the theorem, right? It's by assumption. You see this? The AIs goes to 0 for as N goes to infinity. So that those terms are gonna, this is a subsequence, right? A sub 2n plus 1 is a subsequence of the sequence an. If the whole thing goes to 0, certainly this is also gonna go to 0. In particular, it's convergent. So you can split the sum. You can say this then. A sub 2n plus 1, right? Okay. And now by condition 2, as we just discussed, by condition 2, this is 0. This is 0. So by condition 2, this guy is 0. Now what's this guy? What's the limit of the even partial sum? What's the limit of the even partial sum? We call it S. We call it S, so this is S. So S plus 0 is S. So what did we show? We've shown that the limit of the odd partial sums is also S, right? So the even partial sum goes to S, and the odd partial sums goes also to S. By the previous exercise, the one written in green here, by the previous exercise, we can say that the full sequence of partial sums is also converging to that limit L, which is S in our case. Okay. So by the previous exercise, thus, by the previous exercise, the full sequence Sn is also converging to S, right? So that is the limit as n goes to infinity of Sn is S. Okay. And what's the limit of the sequence of n partial sum, the nth partial sum sequence? The limit is by definition the sum of the series. So that is the series minus 1 to power n plus 1 an is equal to S, right? And this is where n starts from 1 to infinity. Correct? All right, and this implies, or it means that the sequence or the series, the alternating series minus 1 to power n an is convergent as wanted, right? That's what we wanted. So that shows it then. Okay, that shows what? That shows the theorem, the alternating series test. Okay, this test right here. Okay, so the alternating series test, if you have a series whose terms are decreasing in absolute value to 0, then the series must converge. And by the way, let me just point out the following. You see this condition 1? So we requested too much, in the sense that we requested the whole sequence an to be non-increasing, right? So what if we take this out and we replace it by, instead of asking all of it to be non-increasing, how about asking from a certain rank on that this happens? So for all n greater than or equal to n naught, for some n naught. What does this mean? This means that what I'm saying is, the first few terms of the sequence, AIs, the AI sequence, if the first few terms do not obey this inequality, but from a certain rank on, eventually the sequence starts being non-increasing, then the same conclusion is gonna hold, right? Why? Because look, you can run this alternating series that we just proved, but instead of having for all n bigger than or equal to 1, you have it for all n bigger than or equal to n naught. So which means you're gonna show that the series, which is gonna start at n naught, right? At n naught, that's gonna converge. And once you have that this series is convergent, adding finitely many terms to it is gonna also tell you that the full series is gonna converge. Does it make sense? So my point is, if the sequence AI is not entirely non-increasing, but it's non-increasing from a certain rank on, the same conclusion still holds, because as we said, if you run the same program that we just had, the same proof, but instead of having n naught, instead of having 1, you have n naught. So you're gonna be able to show that this series is gonna be a convergent one. And how does this differ from the full series? It's just by adding finitely many elements. And adding finitely many elements to a series that converges is certainly a convergent series, and hence you get the full series is also convergent, right? So you get the entire thing still convergent. All right, I just wanted to point this out just in case we encounter such a situation. All right, let's apply this theorem. All right, example 1. Test each of the series for convergence or divergence. The first one, series whose terms are minus 1 to the power n plus 1 divided by n. You see the series? This is reminiscent to the series whose terms are 1 over n, the harmonic series, right? But now the terms are going to alternate in sign, and that's going to be referred to actually as an alternating harmonic series. Okay. All right, so how do we show that? How do we determine whether this is going to converge or diverge? We're going to run the test that we just learned, the alternating series test. This is certainly an alternating series. So part 1, it's an alternating series. What's this series, by the way? The first term, when n is 1, the numerator is 1, and the denominator is 1, so that's going to be 1, right? And when n is 2, the numerator is going to be negative 1, and the denominator is going to be 2, so minus half. And then the third one is going to be plus 1/3 minus 1/4, as you can check, plus etc. Correct? So what can you say about the AIs here? The AI is 1 over n. So certainly the AIs, the 1 over n, is decreasing the sequence. So because the an is greater than or equal to the 1 over n plus 1, it's certainly bigger, but what's bigger is bigger than or equal, right? And this is for all n. And moreover, the limit, so condition 1, I'm not going to write 1 because it matches this one. So condition 1 of the alternating series test is going to be verified. And in addition, the limit as n goes to infinity of 1 over n, the AIs, go to 0, right? Go to 0. So by the alternating series test, we can infer that the series is convergent. Correct? Makes sense. So because it's a because the AIs are non-increasing, so they are decreasing in some sense, and they go to 0. Very good. Next, part 2. What is it? This one. Look at this series. Certainly the terms alternate in sign, and this is the AI. This guy is the AI, right? So this is AN. What can you say about the limit of AN? AN in this context goes to 3 over 4, right? It doesn't go to 0. So the second condition of the alternating series test is not checked, is not verified. So the alternating series test cannot be applied then. Because remember, for the alternating series test to be applied, you need two conditions. You need that the sequence, you need the AIs to be positive, obviously, and you need those terms decrease to 0. Well, they don't even go to 0. Forget about decreasing. Correct? So the alternating series test doesn't apply. So we are on our own. We have to figure out what to do in this case. Well, look. So in this case, let me copy the series. The series starts at 1, minus 1 to power n, 3n divided by 4n minus 1, right? This is the series. And we call these guys, AIs. Okay. What can we say about this one? The limit as n goes to infinity of an is 3/4, right? Which is not 0. Correct? So those guys goes to a number which is not 0. What can you say about the limit of the whole thing then? The whole thing. Well, the whole thing is not gonna exist, right? The whole thing is not gonna exist. How about we call the whole thing? How about we call the whole thing here xn? So the whole thing, if an does not go to 0, the whole thing is gonna alternate. It's not gonna go to 0. It's not gonna exist, right? It's gonna alternate between 3/4 and minus 3/4. So that thing is not gonna exist. Makes sense? So as such, by the test for divergence, the series is not gonna converge, it's gonna diverge. Makes sense? So let's try the details. So then, the limit as n goes to infinity of xn is not going to 0. It's not going to this, as we said, this is not going to exist altogether, but let me just make a better argument for you. Certainly it's not going to 0, because if it were to go to 0, so otherwise, if this guy were to go to 0, what's the difference between xn and an? What's the difference between xn and an? Do you agree that xn in absolute value is an? Do you agree with me? Since an are positive, do you agree that the absolute value of xn, which is the absolute value of the whole box, that guy is going to become 1 and that guy is an? Do you agree with me? So because otherwise, xn, which is the absolute value of xn is an for all n, since an is positive, as we said. And we said otherwise, which means if this fails, which means if this is 0, then so we have this, and hence what can be said about this? What can be said about, let me do it this way. What can we said about this one? Well, this one, as we said, this is the limit as n goes to infinity of the absolute value of xn, right? The absolute value of xn. And the limit of the absolute value is the absolute value of the limit, because the absolute value of function is continuous, right? Because the absolute value function is continuous. Remember this property? Which property I'm referring to? I'm talking about this. Remember the property that if you have a function that's continuous at a number a, let's say. So if a function is continuous at a and xn converges to a sequence xn converges to a, then the image of the sequence is also going to converge to the image of the limit, right? Remember this theorem? That's what we're talking about here. That's what we're talking about here. The absolute value function is the f, and the a that we're talking about is actually 0. So since xn, so we're assuming that we're talking otherwise, right? We're assuming that xn goes to 0. So the absolute value of xn is going to go to the absolute value of 0, which means 0, right? That's what we're talking about. So, and the absolute value of xn, as we said, is an. So an must also go to 0. Make sense? By this theorem, this is in the sequence section. All right. Okay, so we get this then. We get this, and this is not true because an is 3/4, which is not 0. So this is a contradiction. Okay, this is a contradiction. All right, so our assumption, the otherwise assumption, allows us to reach a contradiction, which means that this must hold, which means that xn doesn't go to 0. And what can you say about a series whose terms do not go to 0, and the terms are given by xn here? Such a series is divergent by the test for divergence. Okay, so thus the limit as n goes to infinity xn must not go to 0. Okay, we wrote this. Thus the series whose terms are xn is divergent by the divergence test. Okay, divergence test learned in the series section. Okay, so long story short, part 2, this series, as we said, is divergent. Okay, part 3. Part 3 has terms that look like this. -1 to power n plus 1 times n2 divided by n3 plus 1. All right, I'm not going to do this. I'm going to leave it as an exercise, but I'm going to give you the hint, or I'm going to discuss how to approach it. So certainly this is an alternating series because the terms alternate in sign. All right. Where do these are the ANs in this case, right? Let me highlight it first for you. So these are the AIs in this case. So this is AN. The ANs of what? Of the alternating series test and the theorem, the statement of the theorem. So these guys are the AIs. Certainly these guys are positive. Certainly they go to 0 because the leading term upstairs is of degree smaller than the guy downstairs. And if n goes to 0, the whole thing is going to behave as 1 over n, right? So that whole thing goes to 0. So condition 2 of the alternating series test is going to be verified. Now, the first requirement to apply the alternating series test is that these AIs to be eventually non-increasing, right? So you want to show that an plus 1 is less than or equal to an for all n, starting from a certain rank on. How are you going to do that? One way to do it is to look at the related function, which is x squared over x cubed plus 1, and show that that function is going to be decreasing. It's going to be decreasing from a certain rank, from a certain x on, from a certain positive x on. Correct? So you're going to look at fx, which is x squared over x cubed plus 1. And you're going to be able to differentiate the function f prime. You're going to find a function which is going to be negative from some number x positive onward. Okay, and to be particular, that x is going to be a cube root of 2. So from x being cube root of 2 onward, that f is going to be a decreasing function. And as such, those terms are going to be decreasing from n equals 2 onward. Okay, because cube root of 2 is between 1 and 2. So the AIs are going to be decreasing, the sequence AI is going to be decreasing from n equals 2 onward. But we don't, I mean, even though the series starts at 1, we said as long as the AIs start being decreasing eventually, that's good enough, right? We discussed this above. And that's going to happen. When n is bigger than or equal to 2, the AIs are going to be decreasing or non-increasing. And as such, the two conditions of the alternating series test are going to be verified, and hence you get that the full series is going to be convergent. Okay, so the series in part 3 is a convergent series. Very good. Okay. All right, so let's look at this next discussion in blue here. So far we have convergence tests for series which have positive terms, as in the previous sections, and for series whose terms are alternating, okay, in sign. However, what if the signs of the terms do not switch back and forth in a regular way, like we discussed in the alternating back and forth? How about they don't alternate, okay? But they still go back and forth between positive, negative, but the idea is without pattern, in an irregular manner. The next idea, which is the idea of absolute convergence, is going to help in such cases. What's the notion of absolutely convergent? This is the definition. So a series is called absolutely convergent if the series of absolute values is convergent. Okay? What's the difference between those two series? The terms of this series are the absolute values of the terms of this series. Right? So we say that a series is absolutely convergent if the series whose terms are made of these guys, but now with absolute values, is convergent. So it's not hard to see that when the AIs are positive, the notion of absolutely convergent and convergent becomes the same because the absolute value of positive number is itself. Correct? This is the next comment. So if the AIs are positive, then the absolute value of those guys are themselves, right? Are themselves. So the absolute convergence becomes the same as convergence. These two notions are the same. Okay, determine whether the series given by this is absolutely convergent. All right. Well, for this to be absolutely convergent, so it is absolutely convergent, means that this guy an absolute value now, right, is convergent. Makes sense? By definition, this is just the definition. I don't like the wording here, so what I mean here, it is absolutely convergent. All right, being, I should say, maybe. Being absolutely convergent means, so being absolutely convergent means that the series whose terms are the absolute value of these guys is convergent, right? Okay, and what's this series? What's this series here? What's this series here? But this guy, no matter what n is, this guy divided by n squared is equal to 1 over n squared. Make sense? because the absolute value of the numerator is 1. And the absolute value of the denominator is n squared. So that guy is this guy for all n. So what's this series then? It's going to be this series, and this series converges because it's a p series. It's a p series with p equals 2, right? So it's convergent since it's a p series with p being 2. All right? And we've discussed this before, right? Okay. The next one, next example. So we know that the alternating harmonic series, remember this in example 1 above? We show that this series is verifies the conditions of the alternating series test, and as such, that series is going to converge. But it's not absolutely convergent. Why? Because what's the absolute value of those terms? The absolute value of those terms are simply the terms of the harmonic series, right? So because the corresponding series of absolute values is the harmonic series itself, and it's therefore divergent, right? So if you put bars here, you get 1 over n. So it's a p series, if you wish. P series where p is 1, and we know that the p series converges if and only if p is bigger than 1, so that's going to diverge. Okay, so this series is convergent but not absolutely convergent. Such series are going to be referred to as conditionally convergent. That's the next definition. Okay, so that's the next definition. A series every time I call series, Siri responds. Anyway, so a series sigma an is called conditionally convergent if it's convergent but not absolutely convergent. Okay, so one more time, a series is called conditionally convergent if it converges without the absolute value and it diverges with the absolute value. Make sense? Like we just discovered in example 3 above. So that series here is convergent, but if you put the bars, it fails to converge, so as such, it's not going to be absolutely convergent. Those series are referred to as conditionally convergent series. Okay. So example 3 above, this example that we just discussed, shows that it's possible for a series to be convergent but not absolutely convergent. The next theorem is going to tell us that the absolutely convergence concept is going to imply convergence. So absolutely convergence is a stronger notion than convergence in the sense that it entails it, right? It forces it. Okay, let's see the detail. Every series which is absolutely convergent must be convergent. So if a series converges, if you put the bars around its terms, then if you drop the bars, it's going to also converge. This is what the theorem is saying. Let's try to prove this theorem. How do we prove this one? So the proof of this, well, the very first thing I want to ask you to observe is for all n, what can you say about an plus its absolute value? Well, if an is positive, that's going to be positive plus a non-negative. Certainly this whole thing is positive, right? Let's talk about an being non-negative. If an is non-negative, that's non-negative an plus absolute value of a non-negative number is itself. So that thing is going to be non-negative. So that thing is non-negative if an is non-negative. Now, if an is negative, if you add it to the absolute value of that an, of that number, the absolute value of a negative number is what? It's minus that number, right? So this whole thing becomes an minus an. And what's an minus an? Is 0. So in both cases, whether an is positive, non-negative, or negative, In both cases, that's going to be 0 or more. Agree? On the other hand, an is less than or equal to its absolute value, right? Every number is smaller than or equal to its own absolute value, because that's the best it gets to. So an is less than or equal to its own absolute value, the absolute value of an, and that guy is itself. So this whole sum is less than or equal to absolute value of an plus the absolute value of an, because again, that guy is less than or equal to this, and that guy is itself. So the sum is going to be less than or equal to twice that thing. Make sense? Okay. All right. And then since we're assuming that the series is absolutely convergent, so since we're assuming that this guy is convergent, right? This is we're talking about the proof of this theorem. So we're assuming that the series is absolutely convergent. So we're assuming that the series whose terms are the absolute value of an is convergent. What can we say about this? This is also going to converge because if you remember one of the properties we mentioned in earlier sections, that thing is going to actually be twice that thing, right? Whatever this number is, that thing is going to be twice that number, because you can push that 2 outside as we discussed before in a different video, right? So that thing is going to also converge. So it's a number. That's my point. That thing is a number. All right. And as such, what can you say about this series? This series has terms which are non-negative. This series has, or those terms are non-negative. So what can you say about this series? What can you say about this series? The terms are non-negative, and the terms are bounded above by the terms of another series which converges. Okay, so let's try it again one more time. This series, whose terms are an plus absolute value of an, are on one hand non-negative. On the other hand, they are bounded above by numbers or terms of a convergent series. So by the direct comparison test, that series is going to converge. So it's convergent by the direct comparison test, right? Direct comparison test. Makes sense? I mean, revisit the direct comparison test. It says that if you have a series whose terms are positive, well, being positive or non-negative, you can just throw away those which are 0. You only get the positive terms, and that are bounded above by terms of a series whose which is convergent. As such, the series whose terms are the dominated ones is also convergent. Okay, all right. And lastly, if you have an, you can rewrite it as an plus the absolute value of an minus the absolute value of an. Am I correct? So you can write it as such. And if you now want to let you sum them up, where n, this happens for all n, right? Without this guy. So what I'm saying is this happens for all n, right? And if you sum them up, where n starts at 1 all the way to k, say, it's a finite sum, you sum up the whole thing here, right? Where n starts at 1 all the way to k. Because what we had before, it holds for any n. As such, if you sum them up for any n, and for those n, I'm talking about those n's which are from 1 to k, you get this, right? So you get that this sum holds for all k. Makes sense? For all natural numbers k. which means that this guy is equal to, this is a finite sum. You can split the sum up from 1 to k, an plus the absolute value of an minus sigma n goes from 1 to k, absolute value of an, right? So we split that up because it's a finite sum. You can just can group them the way you want, because what is it? Addition is associative, right? Okay. All right, and then what? This holds for all k. This holds for all k. How about we let k go to infinity now? If you let k go to infinity, what do you get right there? So at the limit, when k goes to infinity, this guy becomes the full series. So the full series from 1 to infinity, an. And this guy becomes the limit of this difference. But what do you know about the limit of this guy? Well, this is a convergent series. We talked about it above. This is convergent. And this is also convergent. So the limit of this difference is going to be the difference of the limits. And the difference of the limits, when k goes to infinity, that goes to infinity, and that goes to infinity. So you get this. You get this. Agree with me? And now take a look. What do you know about this whole thing? What do you know about this whole thing? Since you know that the series is convergent, this is certainly a finite number, right? This is certainly a finite number. And what do you know about this guy? You're assuming that the series is absolutely convergent, so you're assuming that this guy is finite. So you're assuming that this guy is finite as well, right? So this guy is finite, this sum is finite, and this sum is finite. Subtracting two finite numbers remain a finite thing, right? So long story short, this sum is finite. What does it mean that this sum is finite? This series is has a finite sum. This means that the series converges. And that's exactly what we wanted. That's exactly what we wanted. We wanted the series to converge. Okay, so this is the proof of this theorem. Again, let's read the statement of the theorem once again. If a series is absolutely convergent, which means in bars, if this is convergent, then the series is convergent, which means without the bars, the series is convergent, as we showed, right? The last example of this section, example 6, determine whether the series, whose terms are cosine n over n squared, is convergent or divergent. So this series has terms which are positive and negative, right? Cosine may be negative sometimes and may be positive sometimes. So that term is so that series has positive and negative terms, right? But they're not alternating. They're not alternating. As a matter of fact, the first is positive and the next three are negative. Okay? And so, I mean, the signs are changing in a very irregular manner, and as such, we cannot use the alternating series test because the terms are not alternating in sign. Okay, so but we're gonna what we can do is we can talk about the absolute value of these terms. We can talk about the absolute value of these terms, and if we manage to show that the series with the bars is convergent, which means this series is absolutely convergent, then the series is gonna converge. That series is convergent by the previous theorem, because every series which is absolutely convergent happens to be convergent by the previous theorem. Okay, so that's what we're gonna do. We're gonna try to handle it via talking about the absolute value of the terms. So for all n, we know that cosine n over n squared in absolute value for each one of them, this is at most 1 over n squared. Why? Because cosine n is at most 1, right? So the absolute value of cosine n is at most 1 because cosine n is between minus 1 and 1. So we get this, and this is for all n. As such, by the direct comparison test, by the direct comparison test, this series is convergent. Why? Because this series has terms which are non-negative, okay, for all n, and its terms, those terms, are bounded above by the terms of a series which is convergent. Correct? And that series is technically the p series with p equals 2. So this is convergent since its terms are non-negative and dominated by and bounded above by the terms of a series, the terms of the series 1 over n squared, right? Which is a convergent series because it's a p series with p equals 2. Being a p series with p equals 2. Do you agree with me? So this is the discussion. I'm missing one more parenthesis here. Okay. So we get that this guy is convergent. And what does it mean that this guy is convergent? It means that the series without the absolute value, right? Without the absolute value is absolutely convergent. So therefore, the series whose terms are cosine n divided by n squared is absolutely convergent because we showed that we just showed that that series whose terms are the absolute value of the terms of the original series, which is that one, is convergent. That's what we showed. As such, this is absolutely convergent. Correct? And by the previous theorem, what's previous theorem? What's the previous theorem? It's the theorem we just proved right there. Every series which is absolutely convergent must be convergent. So that series which we just showed that this is absolutely convergent must be convergent. Correct? Make sense? Okay, so this is the end of this section.